And now just few words how we can program the FPGA. If we want to program the FPGA, then we need to generate a configuration for it. The configuration contains the content of lookup tables, configuration of interconnection network, and configuration of clock management and another hardware block. So, for example, if we look on the FPGA, or let's say the simplified structure of the FPGA, then the bitstream tells us that our design will be implemented in, let's say, these blocks. So we will know the content of the lookup table. We will know the content. We will know the content of, let's say, the block RAM memories, which are distributed in columns, and then we need to connect these blocks together via the configurable interconnection network. And this is exactly what the bitstream is. It's the configuration of all elements which are implemented or which are provided by the FPGA. Each vendor has its own development tool. We don't have any let's say general tool which can generate the bitstream for all FPGAs because it's just the secret of that vendors, how the bitstream looks like, how it's generated, and so on. So in the case of Xilinx, the development tool is called as a Vivado, and for the case of Intel, it's called as a Quartus. Now, if we want to describe the digital design, then we can use the HDL language. You will see some example later, or we can use more abstract language, which is very typical, the C or C++. This is the language which is familiar for a lot of developers and computer engineers. Or we can use, for example, the BlueSpec, which comes from the Haskell, and it has great power for if you want to express the digital circuit. I will also show you some example how the design in a BlueSpec looks like and how we can translate it.
I have a question here regarding the development tool. For example, if it is Vivado, and it is provided as you buy the FPGA card, or it is free to download.
Yeah. So for example, in the case of Vivado, you can download it from the Xilinx webpage. But after that, it depends on the FPGA, because some FPGAs are, let's say, if you buy FPGA, then you need to buy a license to use it inside of Vivado. This is very typical for the high-end FPGAs, but if you buy some low-end FPGA, then you can use the free version of this tool. So in your case, I think you have the net FPGA. In your case, you will need a license to synthesize the bitstream for this FPGA. It depends on the type. So now a few words about the hardware description language. It's a programming language which is older than me. It's used for the description of digital circuits. It's really highly parallel because it is using the concept of communicating processes, which are let's say clocked by the by a clock signal, and you really need to think differently when you are programming in HDL compared to this programming in a C or a C++. because it's harder to learn, because you really need to think in parallel everything happening in the same time. You are working on a clock level, so debugging is cumbersome. It can be very tricky for a more complex designs, and when you are debugging the HDL code, you are looking on a waves in a simulator, and after some time you are really feeling like that guy from Matrix, which was looking on the code, and he was recognizing what's going on. The most popular HDL languages are the VHDL, which is mostly used here in Europe, and Verilog, which is mostly used in the United States. I will show you the syntax and example of a simple counter later. Now just a few words about the high-level synthesis. High-level synthesis is a new trend because it allows you to develop the digital design faster than in the case of the HDL approach, and this is caused by the higher level of abstraction, because in the high-level synthesis you are not working on a clock level, you are just expressing you are expressing the algorithm you want to implement inside the FPGA. So very typically we have high-level synthesis tools from C or C++. This code is then translated to the VHDL or Verilog. It depends on the tool, but we can have the compiler from a P4 language to the VHDL, which translates the P4 code. After this presentation, I will show you two possible HLS approaches. The first one is using the C and C++, which is easier. It has a bigger group of users, but it doesn't allow us to define the final architecture of generated device. So you cannot decide what component or what code will be connected with other code and so on. So there is also another high-level synthesis or high-level synthesis tool, which is the compiler from the BlueSpec. It's a Haskell-based tool, and it allows us to define also the architecture of the generated device on a higher level. So you are able to have the architecture of generated device in your hand, and you can describe it really, really quickly. Now, let's say that your HDL code is already written, and it doesn't matter if it's generated from the HDL, it's generated from the higher level of abstraction, or if you implement it by hand, because the HDL code is input for the translation of HDL into the bitstream. It has the translation has several steps. The first one is the translation of the HDL code to the RTL. The RTL is acronym for the register transfer level. So so this view is the most suitable, because very typically you don't need to look on the structure of the gates. You just need to see that the AND gate is connected with the OR gate, and the output is connected to the register, and then the register is connected to another asynchronous logic, and so on. So I will show you how the RTL level looks in the Vivado tool. It basically shows how the building blocks are connected together. After that, when we have the RTL scheme, we can start with the technology mapping from the RTL, which is very typically the translation of asynchronous circuits into the lookup tables. The algorithm, the technology mapping algorithm, can identify some, let's say, parts of the code where the DSP can be used, or for example, that we can use the carry chains and so on. So in this phase, the RTL is, let's say, mapped on basic building blocks of the FPGA. After that, we need to place and route all these blocks together on the FPGA. So this step takes the technology mapped RTL. It places the identified blocks on the FPGA and it connects them together. This phase is the most expensive in time and also on memory, because the process for placing and routing is the NP-hard problem. The development tools are the development tools are not using some exact algorithms, and if you run the place and route for several times, then you will get a different. Then you can get a different results. So this is the most time-consuming process, because during this process you need to meet the timing of digital circuit, as we were talking as I was talking before about the setup and hold timing. So these two parameters needs to be met, and there are different kinds of constraints. For example, the timing constraint. The timing constraint when you, for example, express that the design needs to run on 200 megahertz. This infers some maximal delay which has to be taken through the asynchronous logic, and you really need to meet it. If you don't meet the timing, then you need to make some changes into the design. For example, you need to add some pipeline stages to shorten the critical path, and then the timing can be met. So very typically it's a iterative process when you are changing the architecture to get the right performance and to achieve the timing. And after that, when the design is placed and routed on the FPGA, you can generate the bitstream, which is then uploaded into the FPGA. Here we can see the development process in the figure. For the synthesis, which is the transformation from let's say the VHDL or schematic into the RTL. The input for the synthesis can be VHDL or HDL sources. We can also draw some schematics, and we also need to provide the constraints for later phases. The synthesis can be, if the synthesis was successful, then we can use the behavioral simulation to check that synthesis was successful. It's a let's say simulation on a clock level. Then we need to start the implementation phase, when we are mapping to the target architecture and we are placing and routing the digital design on the FPGA. This phase can be in this phase we need to check that the timing constraints were. This is done in the static timing analysis tool. I will also show you how the static timing analysis looks like, and after the place and route phase, we can run the timing simulation, which is also very time expensive, which is very time expensive. And in this phase, we check that the timing is fine, that the digital circuit is working like it was described, and it can take really a lot of time. But in practice, we are fine. We are fine with the behavioral simulation because the transformation from here to here is typically without a problem. So as I already mentioned, each vendor provides its synthesis tool. The synthesis tool generates a bitstream, and it also provides the algorithms and tools to run the map phase and place and route. It also contains a special generator for generation of softcode, so you can use the predefined library of components. For example, you can generate FIFO memories, you can generate network processing blocks, you can generate and configure the digital clock management and so on. Again, I can show you how the work with the generator looks like. And in these days, the standard is also the high-level synthesis tool from higher languages, very typically the C or C++. In this example, you can see how the HDL code looks like. It's a VHDL example of the up counter. So we will start with some library includes. These libraries are defining the data type, which is called STD logic vector. You can understand it as a bus or as a wire. There is also a type STD logic, which can be understood as a 1-bit bus or just a wire. First of all, we need to define the entity, which is the interface of our digital design. So we have output called cout, which is 8-bit wide. We are indexing from 0. And after that, then we have the enable signal, which enables the counting. And then we have a clock signal and a reset signal. After that, we have to define the architecture itself. So there is an architecture block. So we will write architecture RTL of up counter is. We will define the internal cout signal, which is 8-bit wide, and then we will write a process which is run on the clock signal and the reset signal. So this is a sensitivity list, and if any of these signals is changed, of these inputs is changed, then the process is run. So in this example, we can see that we have the up counter with asynchronous reset. So the reset can come between clock cycles, and if the reset is 1, then we will set the value of the counter to 0. Else, if we detect the rising edge of the clock signal, the rising edge is this. This is the rising edge, and this is the falling edge. Then we start this if statement, and if the counting is enabled, then we will count up. And on this line, you can see the assignment of the internal signal, which is this one, to the output. So this is the example of the HDL. As you can see, it looks like a code in Pascal. It has some similarity. It has some similarities with it, but as you can feel, the debugging of higher design, of more complex design, when you have a lot of processes, when you have a lot of blocks, can be very tricky. So this is the end of the first section, when I try to introduce you the FPGA in a nutshell. And so, do you have any questions before the second part of this presentation? So it seems that, huh?
Yeah, yeah. So my question is very naive. Sorry for that. You mentioned about loot, and so I make I see that there is well, it seems to me the common structures are very similar to what we see in the Tofino, where there are a kind of look table that you are able to do at each stage and so on. So is it where we could register, for instance, some kind of routing information, like forwarding information or something like this?
Yeah. Yes, you can. In the lookup table, you can let's say implement this kind of operation, because very typically routers and switches are using the TCAM memory, where you can upload when you can upload for example, when you can upload rules, and when the search key and when the search request is run, then all the rules are searched in parallel. So yes, you can use the lookup tables for implementation of such kind of a hardware.
Okay, and my second question is about you mentioned CLB, and there is a RAM also. So where in our case, which is a network implementation, it is in the RAM. It is in the RAM that we will put our FIB. And is there any competition access to the RAM? Because I think that the CLB is working independently. So well, it depends also of the paths that you implement into the FPGA. But is there any so what do you put into the RAM? Is it our routing table, or is it only some counters or something like this? And is there any competition access to this RAM? So I mean that some CLB could access, and you have a mechanism to protect when somebody is changing the RAM and so on.
Okay, so I try to answer. The memory inside the slice is it's a really small. It typically is one. It's better not to think about this memory element. You don't need to think about this kind of memory as that it is the RAM. It's really it's embedded block inside the slice, and we are using it for the implementation of a synchronous circuit. So, for example, if you want to implement
I understand that, but on the next slide you speak about the RAM.
Yeah. About this. Okay, sorry.
And I thought that the CLB could have access to the RAM, but I may be completely wrong.
No, you are not wrong. The CLB can access to the RAM because for here we have a RAM. There is a CLB, and CLB can be connected to the internal RAM memory using the configurable interconnection network. The structure of or the properties of the RAM memory typically depends on the FPGA, but we can say that very typically the memory has two independent inputs. So you can work concurrently with the memory block from two sides. You have two independent inputs. So you have two independent address inputs, two independent data inputs, data outputs, and so on. If you want to, the CLB can allocate both sides of the RAM memory, or it can use just one side of the memory, or one access part to the memory. If you want to implement a huge memory inside the FPGA where more blocks can access this kind of memory, then you need to also implement some memory arbitration to control these accesses. So you really need to think on the hardware level.
Okay, thank you very much.
You are welcome.